So as I was telling you to imagine assembly of three, say, steel spheres joined with spring. You're throwing that in air. So spring is performing motion like it is extending and getting compressed, and because of the weight of those spheres, the object is also kind of wobbling. It is rotating. Okay, but all these motions can be in a way broken down into certain directions. Like if you can break down those movements of those of that assembly around, say, x, y, and z axis of the Cartesian convention axis. Okay, so what will be the possibilities that the molecule is moving along y, it is moving along the x, or it is moving along z? Okay, now if it is a linear molecule or non-linear molecule, depending on the geometry of the molecule, so we have the movement for the axis as three movements. Okay, it is moving in direction. It may be rotating along, similarly rotating along x, y, and z axis. Okay, so these are another three possibilities. Other possibility is the translational motion. I hope you understand what is translational motion. See, uh, a person, suppose he is throwing a stick, and this is the stick. Okay, this is the stick. Now, when a person throws sticks, the stick will not travel in linear manner as it is. Like both the ends will not travel to parallel to each other. One end will come like this, the other end will go like this, while the stick is moving in one particular direction. This is something like uh, that knife throwing competition and like that, something like that. Okay, so it is translational motion. Okay, all of these may be happening simultaneously. Okay, all of these may be happening simultaneously. So considering these motions, there are few more permutation and combination. If I tell you that right now, we will spend all the lecture in there only. But if you consider all these motions simultaneously, there are different ways in which a molecule can perform repetitive motion, like vibration. Okay, vibration is the repetitive motion, harmonic motion. So the number of possible ways for non-linear molecule to perform vibrations is, it can perform vibrations, it can perform the repetitive motion, harmonic motion, in 3n minus 6 ways. Okay, where n is number of participating atoms in the molecule. For a linear molecule, it is 3n minus 5. Now, 3 degrees of freedom exist along 3 Cartesian coordinates. That's why we say that for any uh, any object there are 3 degrees of freedom along x, y, and z axis. Now, along each axis you can have 3 translational and 3 rotation. So it will count totally for 6 motions of molecules. Now, rotation about the center bond in a linear molecule is indistinguishable. Like suppose there are 2 atoms attached by a bond. Okay, the bond in itself is symmetrical. So whether the molecule is moving along this axis or not, we cannot tell. It cannot be distinguishable. Okay. Remaining degrees of motion represent vibrational motion that we have studied, number of vibrations within the molecule. Now, what are the factors that influence the normal modes of vibration? We have seen now these are the modes of vibrations. For non-linear it is 3n minus 6, and for linear it is 3n minus 5. So in normal conditions, what are the factors that affect these normal modes of vibration? See, there are four factors which tend to produce fewer experimental peaks than would be expected from the theoretical number of vibrations. Like if you consider the molecule as a model, some model in physics, like what I told you to imagine, that three iron spheres connected with spring. If you consider like that, if you consider the charge on atoms, you consider the strength of bond, you consider the distance between the bonds, and you theoretically predict the ways in which molecule will vibrate. Okay. Now, you are predicting it, but the actual peaks that you observe in the experiment, after you take the spectra, IR spectra, there is difference between what you observe and what you theoretically calculate. So there is reason underlying it. Okay. Let us go through those reasons or factors. The symmetry of the molecule is such that no change in the dipole results from a particular vibration. I will explain you this. Uh, let's open a white screen. Suppose a molecule is consisting of three atoms. There is one atom at the center. It is connected to these two atoms. The central atom is connected to these two atoms. Let us shade the other set of atoms so it is different. Now, there is obviously bond between these two, and there is electronegativity difference between two types of atom. Now, if you just consider this bond, okay, just consider this bond, and the bond is stretching and getting compressed. Since there is electronegativity difference associated with this, there is dipole associated with it, and dipole, in dipole, the distance between pole is changing while the charge on them is remaining constant. So I can say dipole moment for this bond is also fluctuating. So everyone will expect that this bond will absorb IR radiation and this bond will be IR active bond. Now, remember till this point, I hope you have understood that you expect this bond to be active, IR active bond. But now there is another bond present in it, which is similarly vibrating. It is having exactly similar atoms, and that is also fluctuating. Suppose the motion of stretching and bending of this bond is exactly opposite to this bond. What I mean to say is, when the this, suppose let us call it as bond A and let us call it as bond B. So when bond forming, stretching and compressing, bond B is also performing stretching and compressing, but in the exactly opposite direction. So the magnetic moment of A and B are in opposite direction and they are cancelling out each other. So do you think this molecule will absorb IR light now? So the answer is no, because for a molecule as a whole, there is no net change in the dipole moment. Although dipole moment is associated with individual bond, it is getting changed. Let's move on to next point, which is the extension of the first point itself. The energies of two or more vibrations are identical or nearly identical. What happens is, if the energies of these two these two bonds or these two types of vibrations within the molecule are identical, the energy absorbed by that particular molecule, it is like confusion. Okay, although the photon will not understand, it does not have eyes where to go, but it will, the molecule overall will uh, give you a situation where that photon, that unit of energy is not sufficient for it to absorb. So exactly when the energy is doubled, that that higher frequency photon or that shorter wavelength photon will be absorbed by the molecule. So theoretically, you will calculate that at say 800 centimeter inverse of the wave number, you expect vibration, you expect a molecule to absorb, but actually in practice it will absorb at 1600 centimeter inverse, exactly double. Okay, so it is, this is the observation that is obtained. Okay, so you got the second reason why your uh, calculated numbers of normal modes is different than observed. Let's move on to the third one. The absorption intensity is so low as to be undetected by ordinary means, that the molecule is absorbing the IR radiation, but you do not have the device, you do not have the detector which is capable of detecting that minor absorbance. So it is limitation related to your detector. Molecule is not behaving strangely, it is absorbing where it is able to absorb, but you don't have machine to measure that absorbance. Okay, so this is the third reason. The fourth region, the vibration energy is in a wavelength region beyond the range of instrument. This is similar to third one, but the difference is you cannot measure intensity in the previous point. Here the instrument is incapable of detecting that wavelength. We are not talking about intensity of wavelength now, we are talking about the wavelength itself. The instrument cannot detect the wavelength. I hope these four factors are understood by you people. If you don't understand anything, please do ask. Now, these are the normal four factors what we have studied. Now, there are certain uh, random observations regarding the IR spectra. Now, in previous slide, we saw what we observe is not what we calculate. Okay, it is something less than that or something more than that. But in IR spectra, many times you observe bands which has no theoretical explanation uh, in the what we can say, in the normal mode of vibration explanation. Okay, we cannot explain those peaks using the theory behind normal modes, so there is some other explanation. Let us see. Occasionally more peaks are found than there are expected based upon the number of normal modes. The occurrence of overtone peaks that occur at 2 or 3 times the frequency of the fundamental peak is one type of example. We have seen what are overtones. In addition, combination bands are sometimes encountered when a photon excites two vibrational modes simultaneously. This we saw in previous slide also, that there are two vibrational modes having the exactly same energy. So if photons impacts the molecule which carries the energy twice of the individual modes of vibration, then both the vibrating bonds will absorb that photon and share the energy. So although for that higher energy we do not have any explanation or any theoretical basis, but still that energy is absorbed by the molecule. Then proceeding further, the frequency of the combination band is approximately the sum of the difference of the two fundamental frequency. Now, students generally do understand what is sum, but they many times do not understand what is the difference. See, in a molecule, suppose one bond is vibrating in one direction, the other bond is directing in opposite direction. Okay, the vibration is symmetrical, but their direction is opposite. Their the magnitude of the dipole moment associated with both the bonds is different. So, suppose one bond is associated with, say, energy units of say 1000, and the other bond is associated with energy units of say 300, but both of them are in opposite direction. So when they combine 1000 minus 300, the molecule will absorb 700 units of energy because they are in opposite in direction. Do you understand this point of view, students?
Yes, sir.
Okay, thank you, Shakil, for feedback. Now, that is also called as, now we are continuing with the same logic. Huh? There is something also called as vibrational coupling. Now, as the name is suggesting, coupling means one vibration is influencing the other vibration within the molecule. Now, this can be imagined as, suppose you have a magnet in your one hand and you are rotating it, you are say moving it, you are shaking it, and in your other hand there is another magnet, but that is held steady. Now, while uh, shaking one shaking one in your first hand, try to bring that magnet near to the other magnet. Imagine that you are bringing it closer. As that shaking magnet come closer and closer to the steady magnet, you will start feeling the force in the another magnet. You will feel that the other magnet is trying to vibrate along with the first magnet. So in this situation, we can say that these two magnets are coupled. Okay, similar things happens with bonds in the molecule also. I will read out now. The energy of a vibration and thus the wavelength of its absorption peak may be influenced by other vibrations in the molecule. A number of factors influence the extent of such coupling. Okay, the bonds which are affecting each other's absorption, each other's vibration, they are called as coupled vibrations. They are called as coupled bonds. Okay, strong coupling between stretching vibrations occur only when there is an atom common between two vibrations. It is very simple. I hope it is very simple for you also to imagine. Suppose all those red spheres are indicating atoms and red lines are indicating bonds. Now, this bond can, it is impossible for that bond to couple with this bond when it is stretching and compressing, but it can definitely couple with this bond because there is a common atom between these two bonds. So the adjacent bonds can couple which are sharing a atom. Interaction between bending vibrations require common bond between the vibrating groups. Now, this bond angle is changing when the molecule is vibrating. Okay. Now, this may affect stretching and I'm sorry, the bending of say this bond because they are sharing this bond in them. So you can say let us call it as theta and let us call it as alpha. So as the bond angle theta is changing, it may affect the can say bond angle alpha when they are vibrating. So for this you require one bond to be common in two bond angles. Suppose there is another angle gamma. Now theta cannot affect gamma, but alpha may affect gamma. I hope this is clear to you. Students, please give me a feedback. Have you understood this?
Yes, sir.
Yes, sir.
Okay, thank you. Now, we are continuing with the same set of points. Coupling between stretching and a bending vibration can occur if stretching bond forms one side of the angle that varies the bending vibration. It means, so this is alpha bond.
This is beta bond.
So for alpha bond, the stretching of this particular bond may affect its its bond angle alpha when it is vibrating. Okay, when it is vibrating, you can consider this as, say, those athletes, those performers who do athletics on ice surface, that ice skating. Okay, uh, when they are bringing their both hands together, when they are moving both of their hands away from each other. Okay, now both these movements affect how slow and how fast they are moving. Okay, obviously, if the bond over here is getting compressed, okay, and simultaneously the bond angle alpha is also getting smaller and larger. If it happens that the atom, this atom is moving towards the central atom of the alpha bond, the movement of that atom when the alpha bond is getting compressed will also get pushed. It will get faster. I hope you understand this physics. When it is coming closer, it will close faster along the bond also. Okay. So the opposite is also true when it is stretching. It will stretch faster when it is going away. Okay. Interaction is greatest when the coupled group have individual energies that are approximately equal. Now this we have covered several times now, 2-3 times before. Little or no interaction is observed between groups separated by two or more bonds. Now this is very similar to NMR also. You have studied NMR in final year. I expect you to remember it. So this is similar to NMR. वहाँ पे भी coupling नहीं होता है if there are multiple bonds separating two atoms. यहाँ पे we are talking about vibrations. Coupling requires that the vibrations to be same symmetry species. Now this is important point people tend to forget. Now, based on the factors that we have studied, modes of vibration, factors affecting them, what is being observed other than the normal modes of vibration, let us take some examples. First example is of CO2 molecules. I will try to explain this molecule. Okay, but for CO2 molecule, the central atom, which may be shown here in blue, is carbon atom, and there are two white colored oxygen atoms. Okay, so CO2 molecule looks something like this, and it is a linear molecule. So the analogy which you see in front of you is applicable to that. Now observe these four diagrams for stretching and bending vibrations, and then I will proceed for explanation. Just observe for now. Okay, now let us consider the infrared spectrum of carbon dioxide. We have seen the molecule, now consider its spectra. Now, I have not included the spectra here, but there are certain observations which is included in the description. If there is no coupling occurring between two bonds, that is carbon oxygen and carbon oxygen, there are two carbon oxygen double bonds in the molecule. If there is no coupling occurring, the absorption peak would be expected at the same wave number as the peak of carbon oxygen stretching vibration in an aliphatic ketone, that is around 1700 centimeter inverse. See what they're trying to say, there is a carbonyl bond in the molecule. So for carbonyl bond, you get one peak at approximately 1700 centimeter inverse. So you are expected to observe that peak. Okay, provided there is no coupling occurring between the two CO bonds. Now, two CO bonds are in exactly opposite direction in carbon dioxide molecule, CO2 molecule. So, if it happens that they are coupling, they may cancel out the magnetic moment of each other. Okay, it may also happen that they are moving in the same direction at a time. So, the net movement of CO2 molecule will increase. Let us see what happens actually, what is being observed. Now, this part is theoretical, what we expect. Okay. Now, let us see what experimentally happens. Experimentally, carbon dioxide exhibit absorption peak, one at 2330 centimeter inverse and the other at 667 centimeter inverse. Now, how can we explain this? Carbon dioxide is having two carbonyl groups, so 1700 पे peak आना चाहिए, but instead you get two different peaks. Now let us try to find explanation to this. Carbon dioxide is a linear molecule. We have seen just now that, and it has got three atoms in it. So because it is linear molecule, it will have these many possible number of modes. So 3n, that is 3 multiplied by 3, 9 minus 5. So you will get 4 normal modes of vibration, which you have seen in the diagram. Two stretching vibrations are possible. The symmetric vibration causes no change in dipole. That means this will cause no change in the dipole. So it will be inactive. That will be inactive. Thus, symmetric vibration is infrared inactive. Moving further, the symmetric vibration produce a change in dipole moment, so absorption is at 2330 centimeter inverse. Now, what is being expected if this vibration occurs like this? We expect it as 1700 centimeter inverse. But when it is stretching and stretching asymmetrically, this vibration is adding the magnetic dipole moment change in the original vibration. So, the overall effect, what you can see is 2300. How much is the difference between 1700 and 2300? It is 600 centimeter inverse. Now, continuing with the explanation, the remaining two vibrational modes of carbon dioxide involves scissoring. Okay, so when we talk about scissoring, it is scissor-like motion. Okay, now this is coming out of the plane, and this is going. Both of them are going behind the plane. Okay. The remaining two vibration modes of carbon dioxide involve scissoring. The two bending vibrations are resolved components at 90 degrees to one another of the bending motion in all possible planes around the bond axis. So whatever you try to perform vibrations for that molecules, it will be very similar to each other. Okay, whether it is scissoring or any other type of motion, it will be similar. The two vibrations are identical in energy, thus produce single peak at 667 centimeter inverse. That's why you observe only two peaks in carbon dioxide. Okay, anyway, we will have to stop here. It is 10:20 already. You have to go in the next lecture. If you have any doubt, you may ask me on WhatsApp. I will give